By default, a large language model is trapped inside a stateless text window. It can generate Python scripts, output terminal commands, and draft file structures, but it lacks the physical connection to the host system required to actually execute them. OpenClaw acts as an orchestration layer, bridging this gap. It maps executable tools to isolated models, granting them the ability to affect the host environment. This mapping operates on an agent skills-compatible architecture. It creates a standardized, secure protocol for teaching an agent exactly what a tool does, how to format the input, and how to read the output. To deploy this system, operators must manage 3 specific mechanics: the file precedence hierarchy resolving conflicts, the load time gating handling security, and token economics of prompt injection. Controlling these variables allows the model to interact with the local operating system and run untrusted code within a secure workspace. In a multi-agent environment, teaching an agent a skill requires parsing 2 distinct rule sets. A skill's location on disk and its visibility to the specific agent are orthogonal properties. Location determines precedence. OpenClaw uses a strict hierarchy to determine overrides. At the top is the active workspace skills folder. Next, it checks project-specific skills, then personal agent skills. Finally, it scans the shared local directory, falling back to the bundled OpenClaw tools. But presence on the disk does not grant permission. Visibility dictates whether an agent is allowed to invoke the tool, and this is controlled by explicit configuration arrays. By default, an agent inherits its tool access from the agents.defaults.skills array, establishing a baseline capability. To restrict an individual agent, operators define an agents.list.skills array in the configuration file. This specific array replaces the default list entirely. Setting this array to empty strips the agent of all capabilities, generating a blank slate regardless of how many tools are installed on the host. Decoupling file precedence from allow lists ensures that developers can install complex workspace dependencies without violating the access controls placed on individual agents. Moving into the skill payload itself, every tool is defined by a skill.md file. This file must contain a specific configuration block, a single-line JSON object nested under metadata.openclaw. The engine parses this metadata block to execute load time filters before the LLM sees the prompt. The OS filter looks at the host operating system. If a tool is built exclusively for Linux, it is excluded from a Windows machine. The requires.env gate scans for required variables, injecting API keys without exposing secrets to the shell. The requires.bins gate validates executable dependencies, confirming the required command line interfaces exist on the path. Because these filters execute before the prompt is built, the agent only receives instructions for tools currently available on the host. This critical step prevents the language model from attempting to invoke commands for missing dependencies or incompatible systems. Third-party skills downloaded from a public registry are untrusted code. To use them, an operator must establish a secure execution boundary. Docker Sandboxing creates an architectural split between host validation and container execution. A tool may pass validation on the host, but lack the binary inside the isolated sandbox. The setup command solves this by pulling required dependencies directly into the secure perimeter. This command is triggered to run exactly once upon initial container creation, mapping the necessary dependencies into the execution space before the LLM begins reasoning. Leveraging this setup protocol requires granting the sandbox network egress to download the packages and a writable root file system to install them. Separating host metadata parsing from container dependency injection allows developers to securely execute unvetted experimental ClawHub tools. The engine validates the logic on the host, but restricts the execution to the disposable sandbox. Moving to the LLM context layer, every equipped local tool carries a deterministic token cost. During the translation phase, the OpenClaw engine parses the eligible skills and compresses their instructions into dense XML schema blocks. This XML payload is injected into the LLM system prompt at the start of a session, defining the specific physical actions the model can take. The engine requires a fixed 195-character baseline block to open the XML schema, plus 97 characters for every equipped skill. Translated into tokenizer economics, this character data costs approximately 24 tokens per skill, plus the length of its descriptions. To optimize this context cost over long conversations, OpenClaw utilizes a session snapshot mechanism. When a skill is edited, the built-in file watcher detects the change and updates the snapshot. This triggers a hot reload of the XML schema for the next agent turn, updating the tool instructions without dropping the active session history. Mastering this token math and the snapshotting mechanism is critical for budgeting LLM context windows. It prevents out-of-memory errors in high-density, multi-agent environments. Zooming out from the isolated mechanics, we can view the architecture of the complete multi-agent workspace. The OpenClaw Skills Engine is a strictly typed execution layer that enforces security gates before a model begins reasoning. The file system precedence resolves version control, ensuring there are no dependency conflicts when deploying multiple tools across a local directory. The agent-specific allow lists and Docker sandboxing lock down execution security, forcing a boundary between the host environment and what the agent can touch. And the XML snapshot injection handles the token economy, maintaining context limits while offering real-time hot reloading. Aligning these three pillars allows an operator to pull third-party code and deploy it directly into the reasoning loop of an LLM. Mastering this deterministic architecture is the mandatory prerequisite for any human operator looking to scale autonomous agent deployments across multimodal local networks.